Hello, Midnight Traveler. Welcome back to the Midnight's Explorer, where we wander through the quietest corners of history, science, and wonder. Tonight, as the world outside your window grows still, I invite you to journey with me into something vast, something that holds you even now as you listen to these words. Tonight, we're going to explore space-time. Not as a textbook might explain it, with equations that dizzy the mind, but as a story, a human story. Because every great idea begins not in the cold precision of numbers, but in the warm, uncertain heart of a person who dared to look at the universe and ask, what if everything we know is wrong? So settle in. Find your most comfortable position. Let the day's worries drift away like autumn leaves on a quiet stream. Because tonight, we're going to travel backward through time and forward through space to discover how humanity learned that the universe is far stranger, far more beautiful, and far more interconnected than anyone ever imagined. This is the story of space-time. Let's begin. Picture a spring afternoon in the year 1895. The city is Aarau, Switzerland, a small town cradled between rolling green hills and the whisper of the Aar River. The streets smell of fresh bread and horse-drawn carriages. Children play in the squares while merchants call out their wares. The world feels solid here, predictable, safe. In a small room above a schoolhouse, a 16-year-old boy sits by a window, his chin resting on his palm. His name is Albert Einstein. Though no one knows it yet, not even Albert himself, this boy will one day change everything humanity understands about reality. But right now, he's just a dreamy teenager who struggles in school. His teachers find him difficult, stubborn, too lost in his own thoughts. He asks strange questions that have no clear answers. Questions like, what would it be like to ride alongside a beam of light? Close your eyes for a moment and imagine it with him. You're running, faster and faster. The wind tears at your clothes. Your heart pounds. You push yourself beyond human limits, beyond the speed of sound, beyond anything imaginable. And suddenly, impossibly, you're moving at the speed of light itself. 186,000 miles per second. You turn your head and there, beside you, is a beam of light. A wave of pure energy, frozen in time relative to you. You're riding alongside it, moving together through the universe. But something feels wrong. According to everything scientists knew in 1895, this should be possible. If you could match the speed of light, you should see it standing still beside you, just as a fellow runner seems motionless when you match their pace. But young Albert feels somehow that this can't be right. Light, he senses in some wordless place deep within himself, is different, special. It doesn't follow the same rules as everything else. And in that moment of confusion, in that teenage thought experiment conducted in a quiet Swiss room on a spring afternoon, the first seeds of a revolution are planted. But we're getting ahead of ourselves. To understand how Albert and humanity arrived at the strange truth of space-time, we must go back further, much further. We must begin at the very beginning of our relationship with these two ancient concepts, space and time. Long before Albert Einstein, long before Switzerland or modern cities or any notion of science as we know it, human beings looked up at the night sky and wondered. Imagine yourself 5,000 years ago. You are in ancient Mesopotamia, in the land between two rivers, the Tigris and Euphrates. The night is vast above you, unpolluted by city lights. The Milky Way sprawls across the darkness like spilled milk, and every star burns with crystalline clarity. You are a shepherd, or perhaps a priest. You watch the sky not just for beauty, but for answers, for guidance. The stars move in patterns, predictable, eternal patterns. They mark the seasons. They tell you when to plant and when to harvest. They are, in their way, a clock. Time. Even then, thousands of years before Albert Einstein, before Isaac Newton, before anyone had names for these concepts, humans understood that something was flowing, something invisible but undeniable. Days turned to nights. Seasons cycled. Children grew old. Everything moved in one direction, always forward, never back. The Babylonians called it Simanu, the appointed time. The Egyptians called it Nehe, eternal time. Every civilization had a word for it because every human being could feel it, the river we all float upon, carrying us from birth to death, from sunrise to sunset, from now to then. But what was it, this thing called time? The ancient Greeks wrestled with this question as they wrestled with all great questions. Heraclitus said, "You cannot step in the same river twice, for it is always changing." Time is flux, movement, impermanence. But Parmenides disagreed. Change, he argued, is an illusion. True reality is unchanging and eternal. Time, therefore, must be something different from reality itself, maybe just a trick of human perception. Aristotle tried to find a middle path. Time, he proposed, is the measurement of change. It doesn't exist on its own. It's what we use to describe the movement of things through space. Without change, there would be no time. And there it was. Even in ancient Greece, 23 centuries before Einstein, the hint of a connection, time and movement. Time and space, two concepts that seemed separate but were somehow mysteriously intertwined. The Greeks had another word, chronos, time, but also kairos, the right time, the opportune moment. They understood that time wasn't just one thing. It had texture, quality. Some moments felt long, others passed in an instant. Time, they knew, was subjective, even as it seemed objective. And space? Chora, they called it. The space that holds all things. Plato imagined space as a kind of cosmic nursery, the receptacle in which all matter and form could exist. Without space, where would anything be? How could anything exist at all? But here's what the ancients believed, almost universally. Space and time were separate, distinct, absolute. Space was the stage. Time was the music. And the universe was the play that unfolded on that stage to that music, with the two never touching, never mixing, never becoming one. This made sense. It felt right. When you stand in a field and watch the sun move across the sky, time seems to pass the same for everyone, everywhere. An hour here is an hour there. A second is a second. Fixed. Universal. Absolute. And space was just empty. The nothing between things. You could measure it, a foot, a mile, 1,000 miles, But space itself didn't do anything. It was passive, still, a neutral container. For thousands of years, this is what humanity believed. And then came Isaac Newton.
Picture a cold English winter in the year 1666. The University of Cambridge has closed due to plague. The streets of London are emptying as death sweeps through the city. But 23 miles away, in a small manor house in the village of Woolsthorpe, a young man of 23 sits by a window in his childhood bedroom. His name is Isaac Newton. He has a shark face, penetrating eyes, and a mind that works like no other. While the world outside crumbles with disease and fear, Isaac is lost in thought. He has papers spread across his desk, drawings, calculations. He's trying to understand something that everyone takes for granted: motion. Why do things move the way they move? Why does an apple fall down instead of up? Why do the planets circle the sun in such perfect, predictable paths? And in this quiet room, during this plague year, Isaac Newton begins to solve puzzles that have haunted humanity for millennia. He imagines the universe as a vast machine, a perfect clockwork. God, he believes, is the divine watchmaker who wound up the cosmic clock at the beginning of time and set it ticking. And everything, every planet, every stone, every falling apple, follows precise mathematical laws. But for these laws to work, Newton realizes space and time must be absolute. Listen to his words, written in his great work, Principia Mathematica. Absolute, true and mathematical time, of itself and from its own nature, flows equably, without relation to anything external. Read that again, slowly. Let it sink in. Time, Newton says, flows the same everywhere, always, regardless of what's happening. It doesn't matter if you're sitting still or racing on a horse. It doesn't matter if you're on Earth or on the moon. Time ticks forward at exactly the same rate everywhere in the universe, like the steady beat of some cosmic metronome. And space? Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Space, too, is fixed, unchanging, a massive, infinite container in which all matter exists. You can move through space, but space itself doesn't move. It doesn't bend or flex or change. It just is. This vision of the universe is beautiful in its simplicity. Everything has its place. Everything follows rules. The universe is rational, predictable, knowable. You can calculate where every planet will be 1,000 years from now. You can predict every motion with mathematical certainty. Newton's vision gives humanity hope, order, control. The universe is not chaos, it's a puzzle, and we have the pieces. For more than 200 years, Newton's universe reigns supreme. Scientists build upon his foundation. They map the stars. They predict eclipses. They send ships across oceans using celestial navigation based on Newton's laws. Everything works. But there's something lurking at the edges of this perfect clockwork universe, something strange that no one can quite explain: light. Because in the late 1600s, as Newton is developing his theories of motion and gravity, he's also experimenting with light. He takes a prism, a simple triangular piece of glass, and lets sunlight pass through it. And there on his wall appears a rainbow. All the colors hidden in white light separated and made visible. Light, Newton concludes, must be made of particles, tiny corpuscles that travel through space like miniature bullets. This fits nicely with his mechanical universe. Everything is particles bouncing off each other according to mathematical rules. But there's a problem. Other scientists, like Christian Huygens in the Netherlands, are discovering that light doesn't always behave like particles. Sometimes it behaves like a wave. It bends around corners. It creates interference patterns. It does things that particles shouldn't do. So, which is it? Particle or wave? Newton dismisses the wave theory. He's so influential, so respected, that most scientists accept his particle theory for over a century. But the question doesn't go away. It festers, because light, as young Albert Einstein will one day realize, is the key to everything. The mystery of light is the thread that, when pulled, will unravel Newton's entire clockwork universe. Now we jump forward. The year is 1865. The place is London. The world is transforming. The Industrial Revolution is in full swing. Steam engines thunder across continents. Telegraph wires stretch across oceans, carrying messages at the speed of lightning. Electricity, once a parlor trick, is becoming the bloodline of civilization. And in a small study, a Scottish physicist named James Clerk Maxwell is scribbling equations that will change everything. Maxwell is trying to understand electricity and magnetism. They seem related somehow. When you move a magnet near a wire, you create an electrical current. When you run electricity through a wire, you create a magnetic field. They're like two sides of the same coin, but no one understands why. Maxwell is a poet with mathematics. He sees patterns where others see chaos, and over years of careful work, he develops a set of 4 elegant equations that describe how electricity and magnetism interact. But then, something unexpected emerges from these equations. When Maxwell combines them in a certain way, they predict the existence of waves, electromagnetic waves that can travel through empty space. And these waves move at a very specific speed. Maxwell calculates it, approximately 186,000 miles per second. He stares at this number. His heart quickens. That's the speed of light. In a flash of insight, Maxwell realizes light is an electromagnetic wave. It's electricity and magnetism dancing together as they ripple through space. All light, from the warm glow of a candle to the distant twinkle of stars, is this same phenomenon. This is a staggering revelation, but hidden within it is something even more profound, something that will eventually shatter Newton's clockwork universe. Because Maxwell's equations say that light always travels at 186,000 miles per second. Always. Regardless of how fast you're moving when you measure it. This seems impossible. It violates common sense. It breaks the rules of Newton's universe. Most physicists simply ignore this implication. They assume there must be some explanation. Maybe light travels through some invisible medium, a substance they call the luminiferous ether, and the speed of light is measured relative to this ether, not to observers. This would save Newton's worldview. Space would still be absolute. Time would still be absolute. Everything would still make sense. And so, at the end of the 1800s, physicists set out to find the ether. They design ingenious experiments. The most famous is conducted by Michelson and Morley in 1887. They reason that if the ether exists, and if Earth is moving through it as we orbit the sun, then we should be able to detect a kind of ether wind, the same way you feel wind on your face when you ride a bicycle. They build an incredibly sensitive instrument that splits light beams and sends them in different directions, then brings them back together to see if there's any difference in their speed. If there's an ether wind, light traveling with the wind should move slightly differently than light traveling against it. They run the experiment. They measure carefully. They check their work. And they find nothing. No ether wind. No difference. Light travels at exactly the same speed in all directions, regardless of Earth's motion through space. The experiment is repeated. Different laboratories, different countries, different times of year. Always the same result, nothing. The ether doesn't exist. But if the ether doesn't exist, then how can Maxwell's equations be right? How can light always travel at the same speed. Physics is in crisis. Scientists propose increasingly convoluted theories to explain the results. Maybe Earth drags a bubble of ether along with it. Maybe objects shrink when they move through the ether, making the measurement impossible. Maybe. None of it quite works. The problem sits there, unsolved, frustrating, like a splinter in the mind of physics. The old universe is cracking. The clockwork is broken, but no one can see how to fix it. No one, except a 26-year-old patent clerk in Switzerland who has been thinking about light since he was 16.
The year is 1905. The place is Bern, Switzerland. Albert Einstein sits at a desk in the Swiss Federal Patent Office, examining applications for electromagnetic devices. It's quiet work, methodical. It leaves his mind free to wander, which is exactly what Albert needs. He's married now. His wife, Mileva, is at home with their young son. They live in a modest apartment. Money is tight. Albert's father wanted him to become an electrical engineer, something practical. But Albert has always been drawn to deeper questions, bigger mysteries. No university would hire him. His professors found him too independent, too questioning. So he works here, evaluating patents, while in his spare time, in the gaps between applications, during lunch breaks, in the quiet hours of evening, he thinks about the universe. He's been thinking about that old question for 10 years now, the question from his teenage years. What would it be like to ride alongside a beam of light? He's learned about Maxwell's equations. He knows about the failed search for the ether. He knows that something fundamental is wrong with our understanding of the universe, but he can't quite see what. And then, one spring morning, something shifts. Albert is taking the tram home from work. Bern's famous clock tower is visible in the distance. He's tired. His mind is wandering, drifting through the same old problems. And suddenly, like a bolt of lightning, like a key turning in a lock, he sees it. The problem isn't with light. The problem is with time. Imagine this with Albert. You're standing at a train station. A train passes by at high speed. Inside the train, someone flashes a light from the back of the train to the front. To the person on the train, the light takes a certain amount of time to reach the front, say, 1 second. But what about you, standing on the platform? To you, the light still travels at 186,000 miles per second. Maxwell's equations insist on this. But the front of the train is moving away from the light. So from your perspective, the light has to travel a longer distance to reach the front of the train. Same light, same train, but from your perspective on the platform, the light takes more than 1 second to reach the front of the train. How can this be? The light either takes 1 second or it doesn't. Time is time. It's absolute. The same for everyone. Unless it isn't. What if time passes differently for the person on the train than it does for you on the platform? What if time itself is not absolute? What if it flows at different rates depending on how fast you're moving? The idea is absurd, radical. It contradicts everything Newton said, everything common sense tells us. But what if it's true? Albert begins to work through the mathematics. He barely sleeps. Ideas flub through him faster than he can write them down. He fills pages with equations, scratchwork, thought experiments, and piece by piece, a new universe emerges. If light always travels at the same speed, as Maxwell's equations and all experiments insist, then time and space cannot be absolute. They must be flexible, relative. They must bend and stretch to accommodate the constant speed of light. Time passes slower when you're moving fast. Space contracts when you're moving fast. Not by much at ordinary speeds. You'd never notice walking or even flying in an airplane. But at speeds approaching the speed of light, the effects become dramatic. This isn't just a quirk of measurement. This isn't an optical illusion. Time actually, truly, fundamentally passes at different rates for different observers depending on their relative motion. Two people can experience different amounts of time passing between the same two events, and both of them are correct. There is no universal now, no absolute moment of the present that spans the entire universe. What is now for you might be the past or the future for someone moving at a different speed far away. Time, the ancient river that carries us all, is not one river. It's countless rivers flowing at different rates depending on where you are and how fast you're moving. And space, the fixed, unchanging stage, is not fixed at all. It expands and contracts depending on your motion. In May 1905, Einstein submits a paper to a German physics journal. The title is modest: On the Electrodynamics of Moving Bodies. Only 26 pages long. No footnotes. No references to other scientists' work. Just pure reasoning built from first principles. In those 26 pages, Einstein destroys the Newtonian universe and replaces it with something far stranger. He calls it the special theory of relativity. Special because it deals with a special case: objects moving at constant speeds. Later, he will develop the general theory, which handles acceleration and gravity. But even this special case is revolutionary enough. The paper is published in September 1905. At first, almost no one notices. Now, let's pause here for a moment. Close your eyes and really try to feel what Einstein has just told us. You are sitting still right now listening to this story, but still compared to what? You're on Earth, and Earth is spinning at about 1,000 miles per hour at the equator. Earth is also orbiting the Sun at about 67,000 miles per hour. The Sun is orbiting the center of our galaxy at about 514,000 miles per hour. And our galaxy is moving through space at, well, movement only makes sense relative to something else. There is no absolute stillness. No fixed point in the universe where you can plant a flag and say, "Here, this is truly still." Everything is moving relative to everything else. And because everything is moving differently, time is passing at slightly different rates for everything. The atoms in your left hand are experiencing time at a slightly different rate than the atoms in your right hand if your hands are moving relative to each other. The difference is tiny, immeasurably tiny at human speeds, but it's real. Time is personal, local, intimate. Every object in the universe has its own experience of duration, its own stream of moments. And these streams flow at different rates, braiding together in ways Newton never imagined. But Einstein's special theory of relativity was just the beginning. It explained motion at constant speeds, but it didn't explain acceleration. It didn't explain gravity. It didn't explain why objects with mass attract each other. And so, Albert kept thinking. For 10 more years, he struggled with an even bigger question. What is gravity? Newton had described gravity mathematically. He showed that objects with mass attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. His formula worked perfectly for predicting planetary orbits and falling apples.
But Newton himself admitted he didn't know what gravity actually was. How does the sun reach across 93 million miles of empty space to hold Earth in orbit? How does Earth's mass reach up to pull the apple down from the tree? It seemed to require action at a distance, some mysterious force that could work instantaneously across empty space. But if Einstein was right, that nothing can travel faster than light, how could gravity work instantaneously? If the sun suddenly disappeared, would we fly off into space immediately? Or would we keep orbiting for the 8 minutes it takes light to travel from sun to Earth? Einstein suspected it would take 8 minutes. Gravity, like light, must have a speed limit. But if gravity isn't an instantaneous force, what is it? For 10 years, this question haunted Einstein. He filled notebooks with false starts and dead ends. He struggled with mathematics more complex than anything he had attempted before. He felt like he was wandering in a thicket of thorns. And then, in November 1915, he saw it.
Imagine you're standing on a trampoline. The fabric beneath your feet is flat, taut, stretchy. Now imagine placing a bowling ball in the center of the trampoline. What happens? The fabric dips, curves, creates a depression where the ball sits. Now roll a marble across the trampoline. What does it do? It doesn't travel in a straight line. It curves toward the bowling ball, following the contour of the dip in the fabric. From the marble's perspective, it feels like the bowling ball is pulling it, like there's an invisible force reaching out across the trampoline to attract the marble. But there's no force. There's just curved fabric. This is Einstein's great insight about gravity. Space, that empty, invisible container Newton imagined, isn't empty at all. It's a thing, a fabric, and mass curves it. But it's not just space that curves. Remember, Einstein already showed that space and time are connected. They're not separate. You can't curve one without curving the other. So what mass actually curves is space-time, a single, unified fabric that holds both space and time together. This is the moment. This is where space and time become space-time, where two ancient concepts, distinct for all of human history, merge into one. Mass tells space-time how to curve. Curved space-time tells matter how to move. The sun doesn't pull on Earth with an invisible force. The sun curves the fabric of space-time around it, creating a depression like the bowling ball on the trampoline. Earth moves in an orbit not because it's being pulled, but because it's following the straightest possible path through curved space-time. It's like rolling a ball around the inside of a bowl. The ball circles around and around not because the bowl is pulling it with a force, but because the shape of the bowl naturally guides the ball's motion. In Einstein's universe, planets orbit stars because stars curve space-time. Apples fall from trees because Earth curves space-time. Every object with mass is sitting on the trampoline, creating its own little dip, its own curvature. And the bigger the mass, the deeper the curve. Imagine now not a bowling ball, but a cannonball, then a boulder, then a mountain. The trampoline bends more and more dramatically. Now imagine something so massive, so dense, that it bends the trampoline infinitely deep. So deep that the fabric tears, creating a hole from which nothing, not even light, can escape. This is what we call a black hole, a place where space-time curves so extremely that it breaks our understanding of reality itself. But we're getting ahead of ourselves again. In November 1915, Einstein publishes his general theory of relativity. The field equations are beautiful, elegant, terrifying in their complexity. Even Einstein isn't sure how to solve them in most cases.
But he makes a prediction that can be tested. If gravity is curved spacetime, then light, which always follows the straightest possible path through spacetime, should bend when it passes near a massive object like the sun. Newton's theory also predicts that light should bend slightly near the sun because gravity affects everything with energy. But Einstein's theory predicts twice as much bending as Newton's. There's only one problem. You can't see stars near the sun during the day because the sun is too bright. You'd need a solar eclipse, a moment when the moon blocks the sun's light, to see stars near the sun's edge and measure whether their positions shift. The next total solar eclipse visible for Earth won't be until 1919, 4 more years. Einstein publishes his theory and waits. World War I is raging across Europe. Millions are dying. Empires are crumbling. The old world is being torn apart. But some things transcend even war. Some questions are bigger than nations. A British astronomer named Arthur Eddington reads Einstein's papers. Eddington is a Quaker, a pacifist, opposed to the war. He's also a brilliant scientist who recognizes genius when he sees it. In 1919, with the war finally over, Eddington leads an expedition to the island of Principe, off the coast of West Africa, to observe the solar eclipse on May 29th. Another team goes to Sobral in Brazil. The day arrives, the moon begins to pass in front of the sun, the sky darkens, stars become visible in the daytime. Eddington and his team quickly photograph the stars near the sun's edge. Then they wait, measuring the photographic plates carefully, comparing the positions of the stars to their positions when they're far from the sun. The stars have shifted, their light has bent around the sun, and the amount of bending matches Einstein's prediction almost exactly. Space and time are curved. When the results are announced in London on November 6, 1919, it makes front-page news around the world. The Times of London proclaims, "Revolution in science, new theory of the universe, Newtonian ideas overthrown." Overnight, Einstein becomes the most famous scientist in the world. But more important than fame, more important than Einstein himself, is what has been revealed about the universe we inhabit. The stage is not fixed. The music does not play at the same tempo for everyone. Space and time, the fundamental fabric of reality, are flexible, dynamic, alive. We live in a universe far stranger than anyone imagined. Now, let's slow down. Take a breath. Let's step back from the mathematics and the history and ask a more personal question. What does this mean for you? You, listening to this story right now in this moment that is uniquely yours. Because space-time isn't just an abstract concept, it's where you live. It's what you're made of. Every atom in your body exists in space-time. Every thought in your mind unfolds through space-time. Every memory you hold is a journey through time. Every place you've been is a location in space. You are, quite literally, a pattern in space-time, a temporary sculpture made from the curvature and flow of the universe itself. Think about that. Your past, every moment you've ever experienced, still exists somewhere in space-time. In your personal reference frame, those moments are past, but they haven't vanished from the universe. They're coordinates on the map of space-time, just as real as the present, just as fixed as a location on a map. And your future? It's already out there too, in a sense, not determined, not written in stone, but as real a part of space-time as the past. You're moving through time toward it, just as surely as you move through space toward a destination. This is what Einstein's theory tells us. The universe is not a series of nows, stacked like frames in a film. It's a 4-dimensional landscape where past, present, and future all exist simultaneously. Physicists call it the block universe. Imagine time as a landscape you're traveling through. Behind you is the terrain you've already crossed, your past. Ahead of you is terrain you haven't reached yet, your future. All of it exists. You're just moving through it, experiencing it sequentially, one moment after another. But here's where it gets beautiful. Because time passes at different rates depending on motion and gravity, your journey through space-time is unique. No one else follows exactly the same path. No one else experiences time quite the way you do. If you've ever been on an airplane, you've experienced this, though you didn't notice. Time passed slightly slower for you up in the sky than it did for people on the ground. Only a few nanoseconds slower. You need an atomic clock to measure it. But it's real. If you've ever climbed a mountain, you've experienced it too. Time runs very slightly faster at higher elevations because gravity is weaker there. GPS satellites have to account for this. Their clocks run faster than clocks on Earth's surface by about 38 microseconds per day. That's enough to throw off navigation calculations if we didn't correct for it. Your head is aging faster than your feet, not by much, only about 90 billionths of a second over a lifetime, but it's real. Every person you've ever loved has their own river of time flowing at a slightly different rate than yours. When you hold someone close, your streams of time align, moving almost in sync. When they travel far away, their time diverges from yours, even if only infinitesimally. This is what space-time means. We are all time travelers, moving through the landscape of reality at our own unique pace, following paths that curve and bend around the mass of the world. We are, each of us, alone in our experience of time. And yet we share the same space-time, the same fabric of reality woven together like threads in a cosmic tapestry. Isn't that beautiful? Heartbreaking and beautiful at once. We are separated by time even as we're connected by space-time. Alone, together, in the universe.
But space-time doesn't just sit there, static and unchanging. It moves, it ripples, it dances. This is something Einstein himself realized shortly after developing his general theory of relativity. If space-time is a fabric that can be curved by mass, then it stands to reason that it can also be disturbed, set in motion, made to vibrate like a drumhead. Imagine dropping a stone into a still pond. Ripples spread outward in concentric circles. The water surface, which was flat, now has waves traveling across it. Einstein predicted that massive objects accelerating through spacetime would do something similar. They would create ripples in the fabric of spacetime itself, waves that would travel outward at the speed of light, carrying energy and information about cosmic events. He called them gravitational waves. Picture two massive stars orbiting each other, spiraling closer and closer together. As they dance, they stir spacetime like spoons stirring honey. Ripples spread outward from them, invisible but real, stretching and squeezing space itself as they pass. These ripples are incredibly faint, so faint that Einstein himself doubted they could ever be detected. Spacetime is stiff, much stiffer than water or steel or diamond. It takes enormous masses moving at incredible speeds to create waves strong enough to measure. For 100 years, gravitational waves remained purely theoretical. Einstein predicted them in 1916, but no one could build an instrument sensitive enough to detect them. Until 2015. On September 14, 2015, at 5:51 a.m. Eastern Time, something happened in a galaxy far, far away. Two black holes, each about 30 times more massive than our Sun, completed a death spiral that had been going on for eons. They circled each other faster and faster, closer and closer, until finally they collided and merged into a single larger black hole. The collision lasted only a fraction of a second, but in that instant,
The two black holes converted 3 times the mass of our sun directly into gravitational wave energy. 3 entire suns' worth of mass transformed into ripples in spacetime. These ripples spread outward at the speed of light. For 1.3 billion years, they traveled through the expanding universe, passing through galaxies and empty space, through clouds of gas and entire solar systems, their message encoded in the fabric of reality itself. And on that September morning, they reached Earth. At 2 facilities, one in Louisiana, one in Washington State, incredibly sensitive instruments called LIGO, Laser Interferometer Gravitational Wave Observatory, detected the waves. Each facility has 2 tubes, each 2.5 miles long, arranged in an L shape. Laser beams bounce back and forth inside these tubes, and when a gravitational wave passes through, it stretches space in one direction while squeezing it in the perpendicular direction. The amount of stretching? About 1/10,000th the width of a proton. Imagine measuring the distance from Earth to the nearest star, 25 trillion miles, to an accuracy smaller than the width of a human hair. That's the level of precision LIGO achieved. And on that September morning, both detectors, 2,000 miles apart, recorded the same signal within milliseconds of each other. The signal lasted only about a quarter of a second. It sounded like a chirp when converted to audio, starting low and rising in pitch as the black holes spiraled faster and faster before merging. It was quite literally the sound of space-time ringing like a bell. When scientists analyzed the data, they could reconstruct the entire event. 2 black holes, their masses, their spin rates, the distance to the collision, the moment of merger. All of it encoded in the ripples of spacetime. On February 11, 2016, the discovery was announced to the world. Scientists wept. Hardened physicists who had spent decades building these instruments, who had endured years of skepticism and near failure, broke down in tears. Because spacetime, this thing that had been purely theoretical for a century, had finally revealed itself directly. We had touched the fabric of the universe. We had felt it vibrate. Einstein was right. Not just mathematically right, but really, truly, physically right. Space and time are not separate. They are woven together into a single fabric. And that fabric can be stretched, squeezed, curved, and rippled by the dance of matter and energy. We live inside this fabric. We are made of it. Every moment of your life is a coordinate in spacetime. Every memory is etched into its geometry. Every future possibility is encoded in its curvature. And now, for the first time, we can feel the universe breathing. But let's return to something that's been haunting us throughout this story. Something Einstein's theory doesn't fully explain. Why does time only flow forward? Einstein's equations are time reversible. Mathematically, they work just as well if you run them backward. A film of planets orbiting the sun would look perfectly normal, whether you play it forward or backward. The mathematics doesn't prefer one direction over the other. And yet, you remember yesterday. You don't remember tomorrow. Eggs break, but don't unbreak. Coffee cools, but doesn't spontaneously heat up. People age and die. They don't age backward and come back to life. There is a profound asymmetry to time, an arrow that points from past to future, from birth to death, from order to disorder. Why? This question leads us to one of the deepest mysteries in physics: entropy. In the 1850s and 1860s, before Einstein was even born, scientists studying heat and energy developed a new branch of physics. They were trying to understand steam engines and how to make them more efficient. But in doing so, they stumbled upon fundamental truths about the universe. One of these truths is the second law of thermodynamics. Entropy always increases in a closed system. But what is entropy? At its simplest, entropy is disorder, randomness, the tendency of things to spread out, to become mixed up, to lose structure. Imagine a room with all the air molecules bunched in one corner. That's low entropy, highly ordered. Now let the molecules go. They spread out evenly throughout the room. That's high entropy, disordered. And crucially, you'll never see all the molecules spontaneously gather back in the corner. The disorder is permanent. Or imagine a cup of hot coffee. The heat energy is concentrated in the coffee. That's relatively low entropy. As time passes, the heat spreads out into the surrounding air. The coffee cools to room temperature, the entropy increases. And you never see the heat spontaneously flow back into the coffee to make it hot again. This is the arrow of time, the reason we experience a difference between past and future. The past is the direction of lower entropy. The future is the direction of higher entropy. But here's the mystery. Why was entropy low in the past? If entropy always increases, and if the universe has existed for all eternity, shouldn't entropy already be at maximum? Shouldn't everything already be disordered, mixed up at equilibrium? Why does the universe still have structure, stars, galaxies, life after billions of years? The answer seems to be that the universe started in an extremely low entropy state. The Big Bang, the beginning of the universe 13.8 billion years ago, was a moment of incredible order. Everything was concentrated in an infinitely small point. And since then, entropy has been increasing. We are riding the wave of increasing entropy. Time's arrow points from the Big Bang toward the ultimate heat death of the universe, the distant future, when all energy is evenly spread out, when all stars have burned out, when nothing can happen anymore because there's no difference in energy to drive any change. But there's something beautiful hiding in this grim fate. Every moment of complexity, every structure, every living thing, including you, exists because entropy is increasing, not despite it. Life is a temporary eddy in the river of entropy, a local decrease in disorder paid for by a greater increase in disorder elsewhere. When you eat food, you're consuming low entropy energy, organized molecules with stored chemical energy, and converting it into high entropy energy, heat, waste products, movement, thought. You're increasing the total entropy of the universe, but in doing so, you create complexity, experience, consciousness. You're a poem written in the margin as the universe moves from order to chaos.
Now we must venture into even stranger territory. Because Einstein's general relativity, beautiful and accurate as it is, doesn't tell the whole story of spacetime. There's another revolution in physics that happened alongside Einstein's work, one that reveals an even deeper strangeness at the heart of reality: quantum mechanics. In 1900, a German physicist named Max Planck made a troubling discovery. He was trying to understand how hot objects glow, why a poker in a fire turns red, then orange, then white as it gets hotter. Classical physics predicted that hot objects should emit infinite amounts of ultraviolet radiation. They should glow brighter and brighter without limit. This was called the ultraviolet catastrophe, and it was clearly wrong. Hot pokers don't emit infinite energy. Planck found a solution, but only by making a radical assumption. Energy comes in discrete packets, or quanta. Light isn't emitted continuously. It comes in little chunks, like coins rather than liquid. This seemed like a mathematical trick. Planck himself didn't believe it was physically real. But then Einstein used this idea to explain another mystery, the photoelectric effect, and won the Nobel Prize for it. The universe, it turns out, is fundamentally grainy at the smallest scales, not smooth and continuous as Newton imagined.
quantum, pixelated, made of indivisible units. And this graininess applies to everything: energy, light, even matter itself, atoms, electrons. Everything is fundamentally quantum mechanical. But here's where it gets truly strange. In the quantum world, nothing is definite until you measure it. An electron doesn't have a precise position and momentum simultaneously. Before you measure it, it exists in a superposition, a ghostly blend of all possible positions at once. Only when you observe it does it collapse into having a definite location. Particles can be in two places at once. They can tunnel through barriers they shouldn't be able to cross. They can be entangled with each other so that measuring one instantly affects the other, no matter how far apart they are. Einstein hated this. He famously said, "God does not play dice with the universe." He spent decades trying to prove that quantum mechanics was incomplete, that there must be hidden variables underneath that would restore determinism and reality. He never succeeded. Every experiment ever performed has confirmed the bizarre predictions of quantum mechanics. The universe really is probabilistic at its core. Reality really is indefinite until observed. But here's the problem. Quantum mechanics and general relativity don't fit together. General relativity describes spacetime as smooth, continuous, curved. It works brilliantly for large objects, planets, stars, galaxies. Quantum mechanics describes reality as grainy, probabilistic, discrete. It works brilliantly for small objects, atoms, electrons, photons. But what about very small and very massive objects? What about the singularity at the center of a black hole? What about the Big Bang itself, the moment when the entire universe was compressed to quantum scales? At these extremes, we need a theory of quantum gravity, a description of spacetime that incorporates quantum mechanics. We need to understand what spacetime is made of at the smallest possible scales. Is spacetime itself quantum? Does it come in discrete chunks, atoms of space and moments of time? Or is it continuous all the way down? We don't know. Not yet. Some physicists work on string theory, which proposes that the fundamental constituents of reality are tiny vibrating strings of energy. In this view, spacetime itself emerges from the collective behavior of countless strings, like temperature emerges from molecular motion. Others work on loop quantum gravity, which suggests that space is woven from tiny loops of gravitational field, creating a mesh or foam at the smallest scales. The Planck scale, about 10 to the minus 35 meters, far smaller than any atom. Still others pursue different approaches: entropic gravity, causal set theory, emergent spacetime. All are attempts to answer the same question. What is spacetime really, at its deepest level? And here's what keeps physicists awake at night. It's possible, maybe even likely, that spacetime isn't fundamental at all. Just as temperature emerges from molecular motion and pressure emerges from molecular collisions, spacetime itself might emerge from something deeper, something we haven't discovered yet. Space and time, the stage on which all of reality plays out, might be like the surface of the ocean. From a distance, it looks smooth and continuous, but dive deep enough and you find it's made of individual water molecules, then atoms, then electrons and quarks. What are the molecules of spacetime? What is spacetime made of? We don't know. But the question itself is breathtaking, because it means our journey isn't over. The story of spacetime isn't finished. Einstein opened a door. He showed us that space and time are unified, flexible, dynamic. But that door leads to another room, and another, and another. The mystery deepens the further we go. And that's as it should be, because the universe is under no obligation to make sense to us. It simply is what it is, layer after layer of strangeness and beauty, waiting to be discovered. Now let's return to the human scale, to a thought experiment that has captured imaginations for a century. Imagine two identical twins, both 20 years old. Let's call them Anna and Marie. Anna stays on Earth. Marie becomes an astronaut and boards a spacecraft capable of traveling at 90% the speed of light, about 167,000 miles per second. Marie's mission is to travel to a star 10 years light away and return. At 90% light speed, the journey there and back should take about 22 years from Earth's perspective. Marie departs. Anna waves goodbye. The spacecraft accelerates faster and faster until it reaches cruising speed. Marie settles into her journey. She reads books, exercises, thinks about home. She experiences time normally. Seconds tick by at 1 second per second, just as they always have. Nothing feels different inside the spacecraft. After what feels like about 11 years to Marie, she reaches the distant star, turns around, and heads home. Another 11 years pass. She's now 42 years old. 22 years have passed since she left. Finally, Earth appears in her window. She prepares to land. She's excited to see her twin sister again, to share stories of her journey. The spacecraft lands, Marie emerges, and there, waiting for her, is Anna. But Anna is not 20 years older. Anna is not 42. Anna is 52 years old. 32 years have passed on Earth. Marie is 42. Anna is 52. The twins are no longer the same age. This isn't science fiction. This is real physics. Time dilation, the slowing of time at high speeds, is a confirmed, measured, undeniable fact of our universe. Marie has not traveled to the future. She has simply experienced less time than Anna because she was moving at high speed relative to Earth. Her path through space-time took a different route, a shorter route measured in duration than Anna's path. This is sometimes called the twin paradox, though it's not really a paradox. It's simply a consequence of living in a universe where space-time is flexible. But here's what makes it emotionally profound. Marie has genuinely experienced only 22 years. She has 22 years of memories. She is biologically 22 years older. From her perspective, nothing strange happened. But she has lost 10 years of shared history with her sister. 10 years of Earth's history, wars, discoveries, changes, all skipped over. Her friends are older. The world has moved on without her. She can never get those years back. Time is not just different between moving observers. It's genuinely, physically, irreversibly different. And the faster you go, the more extreme the effect becomes. At 99% the speed of light, time slows down by a factor of 7. 1 year for you equals 7 years for someone at rest. At 99.9% light speed, it's 22 to 1. At 99.99% light speed, it's 71 to 1. You could travel for 1 year and return to find everyone you knew long dead. Get close enough to light speed, say 99.999999%, 8 nines, you could travel to the edge of the observable universe.
Now let's travel to the most extreme place in the known universe, a place where space-time curves so drastically that it tears itself apart, a black hole. Imagine a star, a massive star, perhaps 20 times more massive than our sun. For millions of years, it burns steadily, fusing hydrogen into helium in its core. The heat and pressure from this fusion push outward, balancing the crushing force of gravity pulling inward. But eventually, the fuel runs out, the fusion stops, and suddenly there's nothing to hold the star up against its own gravity. The core collapses. In less than a second, a region the size of Earth compresses to the size of a city, then a mountain, then smaller, smaller, all that mass crushing down into an infinitely small point. The collapse is catastrophic. The outer layers of the star bounce off the incompressible core and explode outward in a supernova, one of the brightest events in the universe, briefly outshining entire galaxies. But at the center, something stranger remains. A black hole. All that mass, 20 suns worth, compressed into a point of infinite density, a singularity. And surrounding it, an invisible boundary called the event horizon, a point of no return. Get too close to a black hole, cross the event horizon, and space-time curves so extremely that all paths lead inward. Not even light can escape. Once you cross that boundary, your future is inevitable. You fall toward the singularity. There is no going back, because back no longer exists as a direction you can travel. Let's imagine you're falling toward a black hole. Let's make this personal. You're in a spacecraft, approaching the event horizon of a black hole 10 times the mass of the sun. From a distance, it looks like a perfect sphere of darkness, a hole cut out of the star field, surrounded by a glowing disk of superheated gas spiraling inward. As you get closer, strange things begin to happen. First, you notice that your feet feel heavier than your head. You're being stretched, pulled apart by tidal forces. The difference in gravitational pull between your feet closer to the black hole and your head farther away is growing. Physicists call this spaghettification. At this distance, it's uncomfortable, but not deadly. You look back at your spacecraft, which has been following you, but you notice something odd. The light from the spacecraft looks redder than it should. And when you check your radio communication, your colleague's voice sounds slow, deep, drawn out. Time dilation. Your colleague is farther from the black hole than you are. Time is passing faster for them than you are. From your perspective, they're talking in fast forward, though it sounds slow to you because the light and radio waves are being stretched, redshifted by gravity. You continue falling. The event horizon approaches. From your perspective, it takes only a few hours. But if you look back at the universe behind you, something impossible is happening. The stars are brightening, blue shifting, moving faster. From your perspective, the entire future history of the universe is playing out in fast forward. You're watching time itself accelerate as you fall. And then you cross the event horizon. Nothing dramatic happens at that moment. There's no barrier, no wall, no sensation of crossing a boundary. From your perspective, you simply continue falling. But something fundamental has changed. Every direction you can move now leads inward toward the singularity. Away from the black hole is no longer a direction in space. It's a direction in time. Specifically, it's toward the past, and you can't move backward in time any more than you could before. You're doomed, not because of any force pulling you, but because the geometry of space-time itself has changed. Your future, all possible futures, now includes the singularity. Meanwhile, from the perspective of your colleague watching from a safe distance, something very different happens. They see you approach the event horizon, slower and slower. The light from you becomes more redshifted, your movements become sluggish. Time, for you, appears to slow down from their perspective. They never see you cross the horizon. From their point of view, you appear frozen there, getting dimmer and redder, asymptotically approaching the boundary, but never quite crossing it. Theoretically, they could watch forever and never see you disappear, though in practice, the light from you would redshift to invisibility within seconds. Two perspectives, two truths. You cross the horizon quickly and fall to your doom. Your colleague sees you frozen there forever at the edge. Both are correct. Both are real. This is what it means to live in a universe where space-time is relative. Inside the event horizon, you continue falling. The tidal forces grow stronger, you're stretched thinner and thinner, atoms are torn apart, even the atomic nuclei are shredded. And then you reach the singularity, a point where the curvature of space-time becomes infinite, where all our equations break down, where physics as we understand it simply ends. What happens there? We don't know. Our theories stop working. Some physicists believe the singularity represents a place where quantum gravity effects become important, where the smooth fabric of space-time revealed by general relativity gives way to something grainier, stranger, more fundamental. Others believe singularities represent the edge of space-time itself, the place where the fabric tears, where reality ceases to be. Black holes are the universe's way of saying, here, the laws break down. Here, at the extremes of curvature and density, even space-time cannot hold itself together. They are wounds in the fabric of reality, scars left by the violent death of stars, places where the universe's own mathematics becomes infinite and meaningless. And yet they're also beautiful, natural, inevitable. Einstein's equations predict them. Observations confirm them. There's probably a supermassive black hole at the center of every galaxy, including our own, Sagittarius A, 4 million times more massive than the Sun, sitting at the heart of the Milky Way. Black holes are not aberrations. They're features of a universe built on curved spacetime. They remind us that reality is strange, that the universe operates by rules that defy intuition, that space and time, the seemingly solid stage on which existence plays out, can be warped, twisted, even torn by the presence of mass and energy.
But black holes aren't the only place where space-time behaves strangely. The universe itself, all of space-time, is doing something remarkable. It's expanding. In the 1920s, while Einstein was still developing the implications of general relativity, an American astronomer named Edwin Hubble was studying distant galaxies through the most powerful telescope in the world. Hubble noticed something peculiar. Almost every galaxy he observed was moving away from us. And the farther away a galaxy was, the faster it was receding. This wasn't just random motion. There was a pattern, a relationship between distance and speed. Hubble's discovery shook astronomy. If galaxies are moving apart now, they must have been closer together in the past. Rewind far enough, and they would all converge to a single point. The universe, Hubble realized, has not existed forever. It had a beginning. This was revolutionary and controversial. Many scientists, including Einstein initially, resisted the idea. An eternal, unchanging universe felt more philosophically satisfying, less troubling. But the evidence was undeniable. And when Einstein examined his own equations of general relativity, he realized they actually predicted an expanding universe. He had even inserted a cosmological constant, a fudge factor, into his equations specifically to prevent expansion, because he believed the universe must be static. He later called this the biggest blunder of my life. The universe is not static. Space-time itself is expanding, carrying galaxies apart like raisins in rising bread dough. And if space-time is expanding now, then in the distant past, it must have been much smaller, denser, hotter. Rewind 13.8 billion years and you reach a moment when all of space-time, all of space, all of matter, all of energy was compressed into an infinitesimally small, infinitely hot point. The Big Bang. Not an explosion in space, but an explosion of space. A moment when space-time itself came into existence and began expanding. Before the Big Bang, there was no before. Time itself began at that moment. Asking what happened before the Big Bang is like asking what's north of the North Pole.
The question doesn't make sense because before is a concept that requires time, and time didn't exist yet. The Big Bang is the beginning of space-time, the moment when the fabric of reality came into being. Picture it. In the first fraction of a second, the first 10 to the minus 43 seconds to be specific, the universe was so small, so dense, so energetic that quantum effects dominated. Space-time itself was a roiling quantum foam. The smooth fabric Einstein described hadn't yet emerged. Then, in an instant called inflation, the universe expanded exponentially. Space itself grew faster than the speed of light, which is allowed because it's space itself expanding, not matter moving through space. In a tiny fraction of a second, the universe went from smaller than an atom to larger than a galaxy. As it expanded, it cooled. Energy condensed into particles. Quarks formed, then protons and neutrons. Then, after about 3 minutes, the first atomic nuclei, hydrogen and helium, formed in a process called nucleosynthesis. But the universe was still too hot for atoms. Electrons couldn't capture into nuclei. They'd immediately be blasted away by the intense radiation. The universe was opaque, a glowing fog of plasma. For 380,000 years, this continued. The universe expanded and cooled, and then, at a temperature of about 3,000 Kelvin, something remarkable happened. Electrons finally captured into atoms. The universe became transparent. Light could travel freely for the first time. This is the light we see today as the cosmic microwave background. A faint glow coming from every direction in space, the afterglow of the Big Bang, stretched and redshifted by 13.8 billion years of expansion into microwaves. It's the oldest light in the universe, the echo of creation, and it's everywhere, all around us, a whisper of the moment when space-time first became transparent. After this, gravity began to pull matter together. Tiny density fluctuations, quantum ripples from the earliest moments, grew into clumps. The clumps grew into clouds. The clouds collapsed into the first stars. Those stars burned, exploded, seeded space with heavy elements. New stars formed from the debris, galaxies assembled, planets coalesced. And on at least one planet, orbiting an ordinary star in an ordinary galaxy, something incredible happened. Life emerged. Consciousness. Beings capable of looking up at the sky and asking, where did all this come from? We are, quite literally, the universe contemplating itself, made from atoms forged in ancient stars, living in space-time that emerged from the Big Bang, trying to understand the very fabric of reality we're embedded in. And here's something beautiful. We're still in that expanding universe. Right now, as you listen to these words, space itself is expanding. Galaxies are moving apart. The fabric of space-time is stretching. Not fast enough to notice, nearby objects are held together by gravity and other forces. Your body isn't expanding, Earth isn't expanding, even our galaxy isn't expanding. Gravity's stronger than the expansion on these scales. But between galaxy clusters, in the vast voids of space, the expansion is real and measurable. Every second, distant galaxies move thousands of miles farther from us, and the expansion is accelerating. In 1998, astronomers discovered that not only is the universe expanding, but the expansion is getting faster. Some form of energy we don't understand, is pushing space-time apart with increasing strength. We call it dark energy. It makes up about 68% of the total energy in the universe. We don't know what it is. We don't know where it comes from. We just know it's there, written into the fabric of space-time itself, driving galaxies apart, faster and faster. If this continues, and all evidence suggests it will, the universe will keep expanding forever. Eventually, billions of years from now, galaxies outside our local cluster will recede so fast that their light can never reach us. They'll disappear beyond a cosmic horizon. The universe will grow dark, cold, empty. The stars will burn out, black holes will evaporate, and space-time itself will stretch into a thin, cold, near-perfect vacuum. The heat death. The final entropy maximum. the end of time. But that's trillions of years away. For now, we live in a universe rich with stars, planets, and life. A universe in its prime, a universe where space-time is still vibrant, still full of structure and possibility. We are living in the golden age of the cosmos.